The broadcast is now starting. All attendees are in listen-only mode.
Hello everybody, we are going to get started in 1 minute. Hello everyone, thank you for attending day one of the online training. We're going to go for about an hour. Today is an overview of IpTL internal architecture. If you have any questions, feel free to put them into the chat window. There's a section for questions. More than likely, I will not answer questions as we're going through. At the end of today, I will send out a copy of all the slides that we go through. And within the context of that email, I'll answer any questions that came up from today. And then in our next section, which is going to be on August 6th for the day two of the training, we may start off, if there's any questions that seem like we should go through in more detail, we'll start off with that then. So first section that we're going to go through is what is IpTL? We're going to do an overview of the device. Now, internally within the device, we can operate as a full network router, a layer 2 bridge. We have configurable interfaces between layer 2 and layer 3, basically meaning that I can take any of the interfaces, I can connect them to the internal system bridge and use them as a layer 2 bridge interface, or I can detach it from the system bridge and use it as a layer 3 routing interface. And then we'll get into some details on the tunneling technology, the failover capabilities, things like that within the device. Within each of the devices is a full-featured router. You can operate as the DHCP server, DNS server, DNS relay, multiple routing interfaces. We can set up static IP addresses, DHCP server, DHCP clients. We can add multiple static IP addresses to interfaces. Devices support SNMP, wireless, PPPoE, LTE. There's a lot of different failover capabilities within the device, extensive IP filtering and VLAN support. The core of the device is a layer 2 system bridge, which allows you to transparently pass traffic between different interfaces. Basically, any interface that's connected to the layer 2 bridge, you can pass traffic between the interfaces as if it was an Ethernet switch. So it allows you to make bridge tunnel connections to remote networks and attach those to Ethernet interfaces to have a transparent link to remote interfaces. We can do extensive filtering at both the layer 2 and layer 3 levels. So if I'm bridging traffic between Ethernet interfaces and tunnel interfaces, I can also filter at that layer 2 level. We combine bridging and routing into one system. So this diagram shows you, and we're going to talk extensively about this over the 3 days, attaching and detaching interfaces. So if you look at the two interfaces, the tunnel interface and the local Ethernet interface on the left side of the picture, both of those interfaces are attached to the system bridge. So I can transparently pass traffic between the local Ethernet interface and the tunnel interface. On the right side, the uplink Ethernet interface is detached from the system bridge, which means that I can give it its own IP address, and then I can route between the uplink Ethernet interface with its IP address and any other interface within the device. So the core information here is that I can take that uplink Ethernet interface, I can attach it to the system bridge, and now I can communicate on the uplink interface to any other interface that is attached to the system bridge using a layer 2 bridging technology. When I detach an Ethernet interface or any interface, when I detach an interface from the system bridge, that interface can then get its own IP address, and I can route between that interface and any other interface. So you can detach all the Ethernet interfaces and use them all as routed interfaces. I can attach all the interfaces to the system bridge and use it as a layer 2 Ethernet bridge interface to communicate with other interfaces. Within the devices, we also have a secure tunnel. We can do a single or multiple tunnel options, point-to-point, point-to-multi-point. The tunnels can operate at layer 2 with a bridge tunnel, or we can operate a full layer 3 routed tunnel. We also have what we call an IP sharing, where the server side is a bridge tunnel connection and the client side is a routed tunnel connection. We also support bonded tunnels for sharing traffic over multiple ISPs, being able to do failover between physical devices or failover between multiple ISPs. We use TLS security, user-defined ports and protocols, so we can run in UDP, TCP. We can set any port that we want to run. And we have a lot of user-defined security options within the devices to lock down your system and make them very secure. So within the IpTL devices, we combine all of these features. So I can route between interfaces, I can bridge between interfaces, I can set up multiple tunnels to different locations. The devices can all act like a client or a server for the tunnel. We can do bonded tunnel, bonded failover, and we have a lot of features that allow us to integrate in with multiple ISPs, including packet marking and virtual routing tables. So the next section that we are going to discuss is some basic networking concepts associated with the devices. Most of these will be pretty obvious, but I want to discuss some of these networking features and how it relates to the IpTL devices. So we're going to talk about some bridge and routed networks, how they're different. We're going to talk about the available tools within the devices to support bridge and routed tunnel connections. We'll talk a little bit more about attached and detached interfaces. Bridge, routed, IP share, bonded. We're going to walk through all the different tunnel options that are available. Then we'll also talk about STUB and INLINE connection options, and those are physical installation options. So within the devices, we're mixing bridges and routers. Bridges operate at the MAC level, taking the Ethernet packet and deciding what to do with it. Routers operate on the IP level, so stripping off that outer layer of the Ethernet frame, looking at the IP address, making a decision on where the traffic goes based on IP addressing. Within the IpTL devices, we mix these together. So I can have different combinations of some traffic being bridged to a remote network, other traffic being routed to a remote network, or being routed out another interface within the same device. This is done by attaching and detaching interfaces from the system bridge. So if an interface is attached to the system bridge, then we're bridging over that interface. If an interface is detached from the system bridge, we're going to route through that interface. The core of all IpTL devices is the system bridge. So all of the nomenclature within the device. So if we talk about attach, we're talking about attaching to the system bridge. If we discuss detached, we're talking about being detached from the system bridge. Same thing with IP filtering. When we talk about an input interface, we're talking about data coming into the system bridge. When we're talking about an output interface, we're talking about data leaving or going out of the system bridge. Bridges operate based on the MAC level within a packet. So the devices maintain an understanding of what physical devices are on each of the bridge interfaces. And then based on destination MAC addresses, we go through and we make a decision on where to send that traffic. So Ethernet, bridging traffic all operates at the Ethernet level. So whatever is inside that Ethernet frame, we don't really necessarily care about it. So whether you have VLANs or different IP addressing and things like that, all get passed across the system bridge based on the MAC address. So this diagram is just showing that the PC on the left side, as he sends traffic through a system bridge and it reaches the PC on the right side, the source MAC address and destination MAC address are intact. And this is also the case if you're going across a bridge tunnel. Traffic comes in, take the Ethernet frame, decide where to send it. If it's going to go over a tunnel, we encrypt the entire Ethernet packet, send it across the tunnel, gets to the remote end, gets decrypted, and that same Ethernet frame gets dropped onto that network. So bridges pass traffic between interfaces if they're connected to the same Ethernet switch. And so that goes for even if the second device is at the remote end of a tunnel. When we talk in terms of routing, routers are going to operate based on the IP address and route tables within the device. So if I have PCA on the left side trying to communicate with PCC, he's going to send a packet. The router in the middle is going to take that packet apart, look at the destination IP address, make a decision on where he's going to send it, and then he will recreate an Ethernet frame and send it. So the packet that's on the right side, the source MAC address seen by this PC, is going to be the MAC address of this router. And this is just important to keep in mind as you're debugging networks or looking at traffic on a network, whether you're in a bridged or a routed tunnel mode. Will determine source MAC addresses of the devices that are communicating over the tunnel. The devices also support multiple virtual routing tables, which allows you to handle traffic going over multiple ISPs. So here we have a device with 3 ISPs. We can take all the Ethernet interfaces, detach them from the system bridge, give them their own network interface, give them their own gateway, and then we can send different tunnels over each of those ISPs, or we can bond traffic going over those ISPs. When you detach an Ethernet interface from the system bridge, the system will automatically create a virtual routing table for you. So this is a virtual routing table for Ethernet 2 or Ethernet 3. You can also create your own virtual routing tables within the system. So I can create a virtual routing table based on any criteria that I want, give an IP address for the network, give a gateway, and then based on routing rules, I can make a decision on what traffic I want to pass through that virtual routing table. So in this situation, we'll get into this in more detail in one of the next sections, but I can take traffic and selectively based on source interface, destination interface, packet marking, I can say I want this type of traffic to go to routing table Ethernet 2, and I want a different set of traffic to go to routing table Ethernet 3. I'm going to talk a little bit more about attached and detached interfaces, bridge versus routed tunnels, bonded tunnels and failover, and then we're going to get into physical connections within the devices, STUB and inline mode. So we touched on this a little bit. Any interface that is attached to the system bridge, the data passes as if it's connected to an Ethernet switch. MAC address tables define where that traffic goes. We can filter between those interfaces. Detached interfaces, like the uplink Ethernet interface in this diagram, a detached interface can get its own IP address, and then we can route between any other IP addresses within the device. This table just shows attaching and detaching interfaces. So within the within the web UI, you have the ability to go in and decide if an interface is attached or detached. So all the Ethernet interfaces, the tunnel interfaces, those are all configurable. You can attach them or detach them. Wi-Fi access point looks like a local interface. It's typically attached. Wi-Fi client, PPPoE, 3G, 4G, LTE, those are always detached because those are viewed as WAN technologies. So this just shows a larger picture with more of the interfaces attached to the system bridge. Several different tunnel modes that we can run in. So we can run in a bridge tunnel mode. That's the default configuration within the device. All data passes through the tunnel for interfaces that are also connected to the system bridge. A routed tunnel mode acts more like a traditional IPsec style tunnel, where we go through and we define networks that are on each side of the interface. One of the things that we've spent a lot of time on is when you run in a routed tunnel mode, all of the network configuration is handled by the server side. So I can have a server device and multiple remotes, and I can set up all of the network IP addressing at the server end based on defining the client, telling the client what routes are at the server side. I can define what routes are at the remote side, and all that routing information is passed back and forth between the devices during that initial handshake. We can also run in what's called an IP sharing mode. The server side is in a bridged connection. The client side is in a routed connection. So you're routing between different interfaces on the client side, but everything at the head office or the server side is a bridge tunnel mode. And then we also support bonded tunnel modes that we can use for bonding and sharing traffic, or we can also use that for failover capabilities. Bridge mode is the default configuration. It's the easiest to use. All the traffic passes through the tunnel interface for any interface that's connected to the system bridge, unless we set up filtering and block off some of that traffic. Routed tunnel mode is also conceptually pretty straightforward. Operates like a traditional VPN routed connection, network to network connections with different routing. IP sharing is very unique to the IpTL devices. This is something you're not going to see anywhere else. The server side is in a bridge tunnel connection. The client side is a bridge tunnel connection, but is detached from the system interface. In section 2, we're going to go into a lot of detail on IP sharing, and there's a lot of powerful things that we can do with IP sharing in terms of hiding a remote network. So I can have a server connected to my head office network. I can have multiple client networks that all have the same broadcast domain. So I can have multiple client networks that are all using 192.168.1.x/24. And using IP sharing, I can hide the fact that the remote networks are all using overlapping IP address space. We also support bonded tunnel connections, and you can use this for round robin streams-based connections, or you can use it for failover. I would say the majority of the people using bonded connections with our devices are using it for the failover capability. There's a couple of, typically when we install the devices physically, you'll install them either in an inline mode or a STUB mode. When you're using an inline mode, you have 2 connections in the device. All the traffic passes through the device. The device is capable of making decisions on where traffic goes. This is used for compulsory tunnel or split tunnel applications. So I would have an uplink connected, an uplink WAN port connected to an internet router connected directly to the internet. And then on the local side of the device, I've got my local laptops, databases that are all connecting that are going to make access to the tunnel. Now, those devices, that laptop on the left, he can be routed up through the local ISP, or he can go across the tunnel to a remote location. So all data passes through the device in an inline mode connection. One interface has encrypted traffic, and another interface has traffic that's in the clear. Any of the interfaces can be used to create the inline connection mode. In a STUB connection mode, we have a single Ethernet interface which is connected to the network. Data is bridged between that Ethernet interface and the encrypted tunnel that's connected on the device. Typically, this is used on a server side and a stub connection. If you look at the little network drawing on the left, it would allow me to come in without rewiring anything, without making changes to the head office network. I can plug a single Ethernet interface into my network on my server side, and then I can create remote tunnels coming into that server. Traffic comes in through the tunnel, connects to that device, and then can be decrypted and dropped onto the network, giving me direct access to all of the resources that are at the head office network. When we set up a stub connection, we have a single connection to the network, and typically that network connection is connected to the system bridge, giving access to the tunnel interface. Now, I will say, as we go through the next 3 days, you're going to see client-side networks in stub mode, server-side networks in inline mode. So it's not a mandatory hard rule, but typically the head office is a stub setup with a single Ethernet interface connected to the network, and client networks are typically set up inline. So we're going to walk through a couple of the installation options. These are pretty obvious. We support point-to-point connections, one network connected to another network. Remote private networks. So within the network on the right side, there's a smaller network, which is actually part of the network A on the left side. And you can set these up where on the network that's on the right side, you can set it up where that network can communicate with the rest of the physical network that it's connected to. So the devices that are in the upper right corner can talk to the rest of the devices on network B, or you can create a completely isolated network where they can communicate through the tunnel to network A on the left side and not see any of the information on network B. Multiple client networks. So server side, server device with multiple clients. You can set up the devices where client to client is enabled or disabled, meaning that we can set it up where all of the remote networks that are on the right side can see each other, or we can set up the devices where all the remote clients can see the head office, but none of them can see the other client devices. We also have devices that support multiple tunnels to set up mesh network, and this can be used for failover. And then we also support cloud type applications. Typically, this is done with one of our virtual machines set up in the cloud. We support currently AWS, Hyper-V, ESX, VMware, VirtualBox. And then, so basic networking concepts that we went over, bridge versus routed networks, available tools within the device, attached and detached interfaces, bridge routed IP share and bonded tunnel modes, stub and inline connections. And that's physically how we connect everything. And then just to touch on this again, the core of the system is the system bridge. So everything is discussed in terms of that system bridge. So the next thing that we are going to take a look at is connecting to the devices, default configurations, how the configuration space operates within the device, how to communicate with the device when you first get one. So we'll talk a little bit about the features and capabilities, connecting to the device for the first time, the default configuration and the configuration space within the device, and then we're going to take a quick look at the web interface. So the default configuration of the device, everything you see in the picture is internal to one of our devices. The uplink Ethernet interface is detached from the system bridge, and the uplink Ethernet interface has a DHCP client on it. So if you take a device that's in the default state, take the uplink Ethernet interface, connect it into your network, you should get an IP address and a gateway and DNS from your local DHCP server. And that'll give them enough information to create a tunnel to an external location. The local Ethernet interfaces by default are all attached to the system bridge. Because they're attached to the system bridge, you can communicate with the system IP address. That is the IP address that is on top of the system bridge. The system interface, or the system IP on top of the bridge, has a DHCP client, and he also has a static IP address. So if I take a local Ethernet interface on one of the devices that's in the default state, I can connect it to a network. It can get an IP address, gateway, DNS from a DHCP client that is on the system interface, on the system bridge. The system bridge also has a static IP address. So I can give my laptop 192.168.100.100, connect to one of the local Ethernet interfaces, and log into the device using the static IP address 192.168.100.170. And that can be changed. So all the devices by default have a 100.170 IP address. You can go in and change that configuration within your device. The tunnel is in bridge mode, and it creates a tunnel connection to demo.iptechnologylabs.com. So when you have a device that's in the default state, plug it into a network, it should get an IP address from a DHCP server, and then it should automatically create a tunnel to one of our demo servers. And that allows you to take a device that's in the default state, plug it into a network, get a tunnel up, communicate through the tunnel, and you can see the device is operating as expected. So navigating the web interface on the device, in the upper right corner, we always have statistical information, model code, system ID, box uptime, status of the tunnels, and who you're logged in as. In the upper left of the device, we have high-level links that allow you to go into each of the different sections. Depending on the section of the device that you select, on the left side will be a set of links. And in the center of the page is always going to have status information and configuration information. So the configuration within the device, all configuration changes are immediate. So if I change an IP address, if I change a configuration option on the tunnel interface, that change happens immediately within the device. The configuration change that you make is pushed into the running config. All the applications within the device are operating based on the running config within the device. When a device boots up, it checks to see if there's a startup config. If there is a startup config, it copies that startup config to the running config, and then starts up all the applications based on that. Starts all the applications based on the configuration space. If the device has no startup config, he'll copy the default config into the running config and then boot all the applications based on that running config. So whether you have a startup config or not will determine whether you're running from the startup config or the default config. So as long as you have a startup config saved, the box will operate on the startup config. If there is no startup config, he'll copy the default config into the running config, and he'll operate based on the default config. So multiple options for rebooting the device. In the upper right corner, there's always going to be an option to reboot the device. If I hit reboot, it will tell me, it'll give me 10 seconds to cancel the reboot. Also in the lower right corner of the devices, I can set a reboot timer. This is very helpful when you're working on remote systems. So if I'm working on a remote system and I need to make some IP addressing changes and I'm concerned that I may get knocked off of the device, I can save the config. So I know that the device next time he boots will boot into a known good configuration. And then lower right corner, I can tell the device reboot after 5 minutes. I can go in and make some configuration changes on the IP addressing or networking. If I inadvertently lock myself out of the unit, after 5 minutes, it'll reboot and it'll go back to the last saved configuration. If everything is good, I can then go in and cancel that reboot timer. So startup config and saving the config. So when the box starts up, it copies the startup config into the running config, and it'll run based on that config. There's two different places that I can save the config, either in the upper right or the lower left. And saving the config will take my running config and put that in as my save config, which I'll boot on a next boot. Factory default, when I reset the device to factory default, basically what you're doing is you're deleting the startup config. So anytime you want to reset a device to factory default, you hit the factory reset button, which will delete the startup config, and then you reboot the device. if I hit factory reset and delete the startup config, and then I hit the save config button, I will copy the running config onto the startup config. So if you want a factory default, you can hit the factory default button in the web UI and then hit the reboot button, and then you will boot into the default config. Any of the devices that support a push button reset, if you hit that push button reset, it will reset the device to factory default, basically deleting the startup config, and then it will reboot the device. So it does both of them together within the buttons. Uploading new firmware. We have regular releases, both engineering releases and full system releases. Basically, you go to Home Image Management, find the file, choose the file, and hit Upgrade. It takes a couple minutes. Do not unplug power on the device once you start the upgrade. When it starts the upgrade, it will go through, it'll install the new firmware, and it will automatically reboot the device. We can also export and import the config. So if I export the config off of one device, I can import that config onto another device. When we import a config or export a config, what we're importing and exporting is the startup config. So if I have a device and I save the config and I export that config, when I import that onto another device, I am importing that into the startup config space. So when you export the config, you're exporting the last saved startup config. When you import config, you're putting this new startup config in. So anytime I want to import the config into a device, I will import it and then reboot the device so it starts on that new imported config. The devices support multiple login levels, and in day 2 of the training on August 6th, we're going to go into a little bit more detail on the login levels. You can actually create your own usernames. So within a device, you can create your own username, give yourself admin access, and you can delete the admin username, the monitor username. By default, the admin username is a full read-write, allows you to create new users, make any configuration changes within the device. Monitor login, by default, is a read-only view of the system. Allows the user to go in and set up check status, see how the system's operating, but not make any configuration changes. We're not going to do this together, but just as an exercise, take a box that's set up in the default config, plug in an uplink port to the network. The box should get an IP address, should create a tunnel to the demo system. Then you plug in a laptop to the local port, and you can DHCP through the tunnel from our demo network. So you can reset a factory default, plug in your uplink port into your network, plug in your laptop to a local port. You can log into the device using the 192.168.100.170. He's going to automatically create a tunnel to demo.iptechnologylabs.com. You can log into demo.iptechnologylabs.com and see your device connected. And you can log in with a monitor. And we'll go through in the next section, we're going to go through a couple more hands-on configuration things that you can do. We have some documents online that you can use to walk through some of these initial cases and helping you understand the device better. So the next thing that we are going to walk through is compulsory tunnels versus split tunnels. Compulsory tunnel means that you are pushing all of your traffic regardless of the destination. You're forcing everything to go down through the tunnel, which is great for situations where you have filtering or authentication systems at the head office that you want all of the remote networks to use. Split tunnel, in a split tunnel design, traffic that is intended to go to the head office goes through the tunnel and goes to the head office. All other internet traffic gets routed out your local ISP. So we're going to talk a little bit about online resources that are available. We'll define the compulsory tunnel mode. We'll walk through the setup of a compulsory tunnel mode. We'll define the split tunnel mode, and then we will walk through the setup of a split tunnel mode application. And then we're going to discuss the locations of the DHCP servers and gateways within a network and how that affects the tunnel operation that we are in. So you can go to doccentral.iptechnologylabs.com and this is where we keep a lot of different documentation, user manual information, application notes, data sheets, videos on configurations and setup, in a lot of the resources that you'll see, emails that we send out, has a lot of links to specific app notes. So as we go through and develop new app notes, we add them here. As we add new features, we add user manual information. So in a compulsory tunnel mode, all traffic from the remote network passes to the server network, regardless of the destination address, destination MAC address. You can still communicate locally based on how you configure the local system. So if you had an Ethernet switch behind the device on the left side on the remote network, on the client network, devices could communicate directly between each other. But anything outside of that local network, all traffic is going to go through the tunnel. So for the laptop that's on the left side, his default gateway will be the router on the server network. So that when he tries to reach the internet, all his traffic will go through the tunnel and go to the internet out the server side network router. So typical application, again, this is not mandatory, but a typical application, client side is set up for an inline mode and the server side is set up for a stub mode. So you have traffic going through the client device, and on the server side, you have a single Ethernet connection into that network, which allows you to create the tunnel and communicate with that network on the same Ethernet interface. In a typical setup for a compulsory tunnel mode, we have a laptop on the left side who's set up for DHCP. His Ethernet frames pass into his local IpTL device through the tunnel. They get onto the network, and he is communicating with a DHCP server at layer 2 using the DHCP server that's at the head office network on the server side network. To go through and do a test, or to get more comfortable with this application setup, you can go to Techncial Quick Start and Hardware Guides and how to set up a network extension across any internet access. And this document, this app note, will walk you through step by step, kind of show you each of the configuration options within the UI, setting up your tunnels, setting up your networking, all those kind of things. It goes into a lot of detail on how to configure your device for this application. So if you look, the laptop that's on the left side will send a DHCP request. It will go through the tunnel, and he will get a response from the DHCP server at the head office. So makes it a very good installation option when you want to have a single DHCP server. You want everybody in compulsory tunnel mode, all traffic going through and using, either security devices or authentication systems at the main office. In a split tunnel mode, if I am accessing anything at the server side network or the main office, that traffic will go through the internet or go through the tunnel and communicate with the server network. Any other internet traffic, whether it's email, web request, anything that is not destined for the server side network will go through my local ISP. And so this allows me to make use of traffic on my local ISP. I don't have to put all my traffic through the tunnel. I'm only putting traffic through the tunnel that is actually destined for the server side network. In this situation, the default gateway for the laptop that's on the left side is going to be a local device. It can be my local 71, in this instance, my local IpTL device, or it could be my local gateway. But the important thing of a split tunnel is my default gateway is local to my side of the network. Again, with split tunnel, we have the client in inline mode and the stub the server side in stub mode. Not mandatory, but typically how we set it up. In this scenario, we're showing getting a DHCP address from our local IpTL device, and the local IpTL device here is the default gateway for my laptop. So if I want to communicate within the 192.168.101 network, I send my traffic out. If the traffic is going to the head office, it'll go through the tunnel, communicate with the head office. If I want to go to Google or YouTube, that traffic gets sent to my default gateway, which is my local IpTL device, and the traffic gets routed through my local ISP. So for split tunnel, we also have documentation online. So you can go to Techncial, Quick Starts, network extension. This document also walks you through a split tunnel configuration. We have one more section that I want to review today, which is tunnel operation. So this is going to walk you through some of the tunnel configuration options that are available within the device. So this is all based on our TLS tunnel. In one of our next sections, we're going to talk about our FastLink tunnel, which is a new tunnel technology that we have. Handles all the same features as our TLS tunnel, just a little bit newer technology, a little bit easier to configure. So when you log into a device on the client side and look at the status, you get an overview of data passing through. You get status information at the top in terms of tunnel uptime, what my mode is, whether I'm running AutoConnect. Same type of thing when I log in and the device is on this is set for server. I get an overview of all the devices that are connected to me. Also get information in terms of whether we're running in bonding, how many connections are allowed, whether we're in IP sharing mode. Basic configuration, each of the devices can be configured as a client or a server. We can run a UDP TCP, you can enable disable compression or passing toss fields. You can select your cipher. By default, we run AES 256. Tunnel authentication and renegotiation of keys. These are all allow you to fine tune how you want your cipher running, how often you want to renegotiate your keys, which gives you your perfect forward secrecy. We'll talk a little bit more about tunnel authentication coming up. The basic tunnel configuration, you can go in and set up to 4 different remotes. And this creates a very basic failover. If I'm in a server mode, I can set my listen port and I can set my keep alive. So the keep alive, he'll send out a packet checking to see that the remote device is still online. And this is just running in UDP mode. If I'm running in UDP mode, I can determine how long without communicating from the remote device that I determine if I'm in, if the tunnel is up or down. We can also redirect non-TLS traffic. If we determine that this is not something part of our tunnel, we can redirect that traffic somewhere else. And the client allows us to enable or disable the remote devices to see each other. TLS authentication allows me to create an HMAC firewall. Basically, I can put in a custom string here, and it'll create an additional HMAC on the front of the packet. The benefit here is if I receive any kind of communication from a remote device that doesn't have a matching HMAC on the front of the packet, it gets dropped at a very low layer within the system. So he doesn't go through and start doing his TLS handshaking and then decide that this remote device is non-authorized. He can drop that packet very early on in the process. Client-side devices always pass directly out through NAT. Typically, you don't need any kind of rules in your local firewall to get out from a network. On a server side, setting up a manual configuration, you typically set up a port forwarding rule going from the public side to the local side just for the tunnel. So if I had a server that was listening for a tunnel on UDP port 5150, I would set up a port forwarding rule allowing traffic from the outside UDP port 5150 to get to my server device. All of our devices support real-time resource. This is a replacement for dying DNS. The devices are continuously going out, trying to determine what their public IP address is. So if we have a device sitting behind a NAT router, the device will go out similar to dying DNS, determine what his public IP address is. He will publish that public IP address using his system ID. The system ID matches the MAC address of your uplink Ethernet interface. So each of the devices has a system ID. And then if I want to, and then the device will go out, determine his public IP address. He will publish his public IP address as that system ID. And then I can use that on my client devices. So within my client device, I can just determine what my server-side device is and use the system ID for my server-side device as my remote network. So when I set up my tunnels, I can use the MAC address of the server, they will convert this. They'll do a lookup and convert this MAC address into the public IP address of my server network. So when you set up your devices on your client side, you can create a custom URL. You can use the MAC address of the server side IpTL device, or I can use a dotted quad. I can set up different ports that I'm listening to, and we can run in both UDP and TCP mode. IP sharing, we're going to touch on briefly here, just from the perspective of configuring the tunnels. But in section 3 of this training, we're going to go into a lot of detail on how IP sharing operates and how the routing works within an IP sharing. So an IP sharing is a bridge tunnel connection that is detached from the system bridge. So basically we set up a standard bridge tunnel, and then we can go in and detach that interface, apply NAT, and then we can decide how the IP addressing within the system works. So basically what we're doing here is we're setting up a tunnel to a server network. Once the tunnel comes up, we detach the interface, and we're sending DHCP requests down through the tunnel. When we get that DHCP address back, we apply that to our interface, and then we can apply NAT. So any traffic that goes through that interface is using the IP address that we received from the DHCP server at the head office. So I've got a remote device. He's connected to a router. He's got a 172.1.1.15 address. He's got a local side network of 192.168.10. The tunnel gets established with the head office. And once this tunnel gets established, he sends a DHCP request down the tunnel and gets an IP address from the head office DHCP server. So he gets a 10.9.13 address. So now if my laptop, so let's say my laptop has a 192.168.10.10 address. If he tries to access this laptop on the right side, 10.9.13, his traffic will go to his IpTL device. It will get routed out his tunnel and will get NATed using the IP address that he received from the head office network. So what this laptop on the right side sees, he sees a packet to 10.9.13.20 from 10.9.13.15. So now I can take a remote network, connect it to my head office network, and I don't have to have any routing in my head office network for the return path, because all the traffic that I receive from this remote network is going to come from 10.9.13.15. And by doing that, this laptop on the right side thinks that it's local traffic, thinks it's just another PC on his network, and he can respond directly to that traffic. The other benefit here is I can have 10 different remote networks that are all set up as 192.168.10.x. But each of the tunnel interface IP addresses, because it's being gained by DHCP from the head office, each of the tunnel interfaces IP addresses will be unique. So all the overlapping remote networks are all communicating with the head office using a unique IP address. This is just another view of IP sharing. You can look at it as a 3-port router. So I have an IP address on my uplink Ethernet interface that's connected to my local ISP. We have an IP address network on the local side or on the system side of the device. And then we have an IP interface on the tunnel interface. And any traffic that gets routed through the tunnel interface to a 10.9.13 network will get NATed, and the traffic at the remote end will look like it's coming from a 10.9.13 address. To set up IP sharing, set up standard bridge tunnel, and then we can detach it, apply NAT, and we can either set up a static IP address or we can run in DHCP. Allows me to use a small number of DHCP addresses from the head office. So now each of my remote networks are all basically sharing one IP address from the head office network. I can have overlapping IP addresses on the remote side. Also allows me to run in split tunnel or a compulsory tunnel application. The devices support a lot of different VLAN capabilities. We can create multiple VLANs. We can create multiple IP addresses within a VLAN. So I can create any number of VLAN interfaces on top of an Ethernet interface. The other thing that we can do with the devices is we can add VLAN tags to traffic in flight within the device. So if I've got a remote network that doesn't know anything about a VLAN, but my head office network is all running on a VLAN, I can add VLAN traffic as it passes through the device. And so here you can see we've got a local Ethernet interface connected to the system bridge. System bridge is connected to a VLAN interface, and the VLAN interface is connected to the tunnel. So now we've got a head office network with VLAN 101 for its data traffic. I'm adding a new remote network that does not have any VLAN capabilities. Instead of adding a VLAN aware switch on the remote network and adding the VLANs, I can have that VLAN added on the device. So if I looked at the local traffic on the remote network on the left side, there's no VLAN tags. Any traffic comes into the device, which needs to go to the head office. The VLAN tag is added. We encrypt the traffic, send it through the tunnel. When it gets to this side, he's not configured for VLANing, so he decrypts the packet, drops that packet onto the network, and now it's an Ethernet frame with a VLAN tag inside. So you've got one network that doesn't know anything about VLAN tagging, another network that uses VLAN tagging, and we're doing that translation in flight as the data is coming in and out of the tunnel on the remote network. Routed tunnel mode operates like a traditional routed connection. We've added some features that make it very easy to use. So on my server side, I can set up server-side networks. These are networks that live on the head office. When a remote device connects into this server, the server is going to pass to him 192.168.1, 192.168.7, 192.168.15 as head office networks. So when the remote device receives that information, he knows if anybody on his network is trying to reach 192.168.7.x, that he should send that information through the tunnel because the server-side device understands how to access that information. We also set up client devices based on the system ID, and we can give them interface IP addresses, and we can give them a network IP. And this tells the server if anybody is trying to reach 192.168.2 network, send it down this tunnel interface to this remote device because that network lives on his remote connection. The devices support AutoConnect for point-to-point tunnels. So you can do a full AutoConnect, which we would configure at the factory between two devices, send them out in the field, they go out and find each other and create a direct connection. Or you can run a MAC base. So I can take two devices, I can take the system ID or the MAC address of the device and put those into each of the device to peer each other, and they will communicate. So the way AutoConnect operates, I have a system ID for my local device, and I have my peer system ID or my peer MAC address. So this is showing I have the device set for a MAC-based connection, and I'm telling him this is the MAC address of the device that I want you to connect to. So what AutoConnect does is it creates a direct tunnel connection between two devices. There's never a tunnel that goes through one of our central servers, but we do use it like we use a central server to allow these devices to communicate, but it allows them to create a direct connection even when both devices are behind NAT and prior to any knowledge of what the networking looks like. So when the devices start up and they're running AutoConnect, they'll communicate with one of my central servers. They'll send them their MAC address. If it's a full auto, the server will send back who they're going to connect to. If I'm running a MAC base, I'll tell them, here's my MAC address, here's who I want to connect to. The central server sends back information on the peer, gives them an understanding of the public IP address and how the NAT router is operating on that remote network, and then they will create a direct connection between the two devices. So like I said, our devices never create a tunnel through one of the central servers. Central servers are always used just to provide information on how to make a direct connection between the tunnels. Bonded tunnel connections, we can go through and set up multiple connections. They can go to different locations. They can use different ports. They can use different protocols. They can use different ciphers. You're basically creating multiple connections and then linking those all together using our bonded service. Integrated within the bonded tunnel setup, within the port, I can make a packet marking. What this does is any traffic associated with this tunnel internally would be marked 99. Any traffic associated with tunnel number 1 will be packet marked as 100. In the system, I can do IP filtering based on that packet marking. We can also direct traffic out different ISPs based on that packet marking. So if I was doing this as a bonded tunnel setup and I wanted each of these tunnels to go through a different ISP, I would have Ethernet interfaces connected to each of those ISPs, creating virtual routing tables. I would have one tunnel set for a packet marking of 100, my other tunnel set for a packet marking of 99, and then I would create a rule saying, hey, any traffic with packet marked 100, go out ISP number 1. Any traffic that is marked 99, send out ISP number 2. We have the ability to set up round robin, streamed, or failover connections. Round robin and streams-based connections are sharing traffic over multiple bonded tunnel connections. Failover will allow you to create a hot standby and pass traffic over one tunnel unless there's a failure. So here we show a bonded tunnel that's in a failover mode. It shows you 2 out of the 2 tunnels are connected. Shows that we're in a hot standby, and it shows you which of the tunnels is actually passing traffic. That's your active tunnel. If we get a failover, you see 1 or 2 tunnels is connected. The failover is active, and now our active tunnel, our active interface is tunnel 2. So all of our traffic is going through tunnel 2. So that is everything that I had for today. Pretty good on time. We will send out shortly after this, after I close down the webinar, we will send out all sets of the slides for today. You can use the email address or the marketing email address or support at iptechnologylabs.com. As you go through the slides or any questions that came out from today, please feel free to email us. And we'll go through and answer your questions, and feel free to get on Doc Central, go through the documentation, and send any emails with any questions that come up. Thank you very much. And hopefully we'll talk to everybody on August 6th, which is the second day of training. Thank you.